This is Professor Thomas here, bringing you a live video. We are going to be discussing polynomial and rational functions, and we're going to be looking at how to solve the inequalities, polynomial rational inequalities. Here are some of the objectives: solve polynomial inequalities, solve rational inequalities, and then solve problems modeled by polynomial or rational inequalities. Let's begin. So simply stated, a polynomial inequality is any inequality that can be found or that can be put into one of the forms where we have some function less than 0 or greater than 0, less than or equal to 0, or greater than or equal to 0, as you can see there. You will write, if it's not in the form already, you will have to write it in that form, and that will enable you to solve it properly. Let's look at the next step here. So the procedure is to express the inequality in the form f of x is less than 0 or f of x is greater than 0, where f is a polynomial function. To solve the equation f of x equals 0, the real solutions will be the boundary points, okay? And those are, sometimes I'll refer to them as the critical points or the critical values. Those will enable us to create an interval so we can test out certain locations and points outside of the boundaries. So once we have these, we locate these boundary points on a number line, thereby dividing the number line into intervals. Fourth step, choose one representative number called a test value within each interval and evaluate the function f at that number. And we want to see if the statement is true or not. There are certain things that could happen after that point. If the value f is positive, or implies f of x is greater than 0 for all those numbers in the interval, or the value of f is negative for all numbers x in the interval. And then fifth step, write the solution set selecting the interval or intervals that satisfy the given inequality. The procedure is also valid if we were to replace the strict inequality less than symbol with the compounded inequality less than or equal to, and vice versa. However, if the inequality involves less than or equal to or greater than or equal to, include the boundary points in the solution set. Okay, so let's see how this begins. Now that's a lot to take in. That was a huge lecture. Now what we're going to do is follow up that lecture with an example. So here we have this problem. We have, it appears to be a polynomial, looks like a quadratic, and it's an inequality. So the first thing we got to do is put it in the form where the inequality is greater than or less than 0. So it's like setting it to 0. So let's move over that 20. So there's our first step, and let's see how we do that. Okay, there we go. So after we've done that, now we can see what polynomial we're really working with. We're working with x squared minus x minus 20, and so what we're going to do is set that polynomial to 0 and solve for all the x's that make that function 0. Now we can do this a number of ways. This is a quadratic equation, and obviously a quadratic equation can be solved in a number of different ways. You can use the quadratic formula, complete the square, or if you can factor it, you can just factor it and then evaluate each factor. Because x squared minus x minus 20 factors nicely into negative 5 and plus 4, all those two factor pairs, you can factor it and now set each factor to 0. You can solve for x for each factor. X minus 5 is 0, and also you can solve x plus 4 is to 0 pretty quickly, and now we'll get those two critical value points. These are our boundary points. So let's locate these points on a number line now. As you can see, we have the 2 points located on the number line, and that also implies we have divided the number line into 3 intervals. So we have to just test the point on in each interval, some nice point, and that will let us know if the statement holds true or not. If it holds true in one boundary point or one test point, it will hold true in every point in that interval. These are the three distinct intervals. And so now what we'll do is just choose some points to test. So in the first interval, we're going to test -5. And let's see what happens when we plug -5 in. Now, you can substitute it into the function f of x, that function, or you can plug it into the original inequality up here. Oftentimes, this is probably the best procedure to do. Plug your test point into the original and simply state if it's true or false. Like if I plug -5 in there, I'm going to get positive 25 and then plus another 5 because minus x and that -5 minus a -5 turns out to be plus 5. So I get 30, which means it's a true statement. And that also means that this interval satisfies the inequality, so it's going to be a part of the solution set. Let's check another test point. This time we're going to test 0. They're plugging 0 into the other equation and they're checking to see if it satisfies the inequality. It did. And now they're testing another interval point. And see, when you plug this one in, we're getting positive, a positive number. So f of x is greater than 0. And so now we have it. We know where it's positive and where it's negative. So we see that in step 4, based on the intervals that we chosen, f of x is greater than 0 for all x in that interval, and it's also greater than 0 for the interval f to positive infinity. So the solution set will be this interval combined with or unioned with that other interval. And we can even plot this out in or on the number line to show the solution set on the number line as well. As you can see, it does not include the boundary points. It starts at the boundary points, everything less than, and also the other solution set starts at the boundary point and everything greater than. Alright, now what we're going to do is look at the procedure for solving a rational inequality. So the first thing we're going to do is set that rational inequality to 0. And sometimes this takes a lot of work. It's not quite in the 0 form at the moment, but we can move over that one and then simplify it out. It's probably best to work with a single rational function, and so we're going to have to combine like terms here. We're going to have to get a common denominator. That 1 does not have a denominator right now, so we got to multiply the top and the bottom by x plus 1 and then start to simplify it out. Okay, and keep in mind you're going to be subtracting that top part there, so that's going to become minus x minus 1, and then just combine like terms there. Okay, so we did do it. We did transform our original rational inequality into one where it's set greater than or equal to 0. And so we know that we want to check all the x values that will make it greater than or equal to 0. So the next thing we're going to have to do is get our boundary points. So you keep simplifying that down as well. So we got x minus 1 over x plus 1 is greater than or equal to 0. And so basically what we're saying is that we don't have to work with this original problem. We can now work with this one. Okay, let's get that straight. Because they're equivalent to each other. And it's in the form greater than or equal to 0. So let's continue. Now, in order to get the boundary points, we'll set the numerator to 0 and also the points where the function's not defined, the denominator, we have to set that to 0 as well. And all those values will be potential critical values for the functions, the x values that make it undefined and the x values for where it is 0. So let's continue. Well, if we just set the top to 0, we're going to get x as 1. And if we set the bottom to 0, we're going to get x as -1. So it appears we only have two boundary points, -1 and 1. So let's locate those on the number line. Again, it does divide the real number line into 3 distinct intervals. So now we're going to have to test each interval here. Now keep in mind, as we list out those intervals, a couple things happened. Notice that -1 is not part of the domain of the rational inequality because it makes the rational 0, but it is a critical boundary point. But also 1 is part of the domain. X can be 1. It will make it 0, but it's part of the domain. And so what we can do is use it as well. And our other interval is from 1 to infinity. So let's create some test points now. We're going to choose some test points that makes our plug-in numbers easier. So the first thing we'll do is test -2. We have to test a point in this interval. And we don't want to test a point on the boundary. Okay, we already know what's going on at the boundary point. The boundaries satisfy the inequality if they're part of the domain. So we're going to test -2. Now, you do have a choice where you plug it in at. You can plug it into the equivalent form or the original, and you'll be okay either way. In this example, they're plugging it into the equivalent form. It was simplified out quite a bit. So plug it in there and see if it is greater than 0 or not. It turned out it was. Now we're going to check another point. Now, when we plugged it into a test point into the center interval, the middle interval, f of 0 turned out to be -1. So because we got a -1 in the end, we can say that f of x is 0 for every x in that domain. If it's negative for one test point, it'll be negative for all values in that interval because it cannot change direction within an interval. It will only change direction at the boundary point. And that's why we had to get those boundary points. And so now we know that it's negative for all x values in that interval. And now we will test one more point. Let's test 2 in that third interval. And when we plug 2 into the original function there, or the equivalent function, we get a positive number, 1/3. So we can state that f of x is going to be positive or greater than 0 for all x in that interval. And now we're ready to write out the solutions. So the solution set will be these two intervals combined together, or we can write it in set builder notation, and we can even graph it on a number line. Okay, so we now have an application problem, and let's go through it. It says an object that is falling or vertically projected into the air has a height above the ground as s of t in feet given by this formula, -16t squared plus the velocity t plus some position s naught, where v naught is the original velocity, the initial velocity in the object in feet per second, and t is the time of the object in motion in seconds, and s naught is the original height, the initial height of the object in feet. An object is propelled straight up from the ground level with an initial velocity of 80 feet per second. Its height at time t is modeled by s of t is equal to -16t squared plus 80t, where the height s of t is measured in feet and the time t is measured in seconds. In which time interval will the object be more than 64 feet above the ground? Okay. And keep in mind it said more than 64 feet above the ground. Okay? So we do need to set up an inequality to actually do this problem. Okay. So finally, after combing through the problem, we have an inequality, and we have to answer the question. We want to know in which time interval will the object be more than 64 feet above the ground. So what we're going to do is actually carry out the procedure that we use to solve polynomial inequalities. We're going to try to set this guy equal to 0 and then evaluate it out. So when we set it to 0, we want to check then for all t values that make this expression greater than 0 will actually satisfy the original problem. So now we got to get some critical values or boundary points by solving the equation, setting it equal to 0, solving the polynomial equation when it's set equal to 0. Let's do that. Okay. Probably be a good idea to factor out a negative 16 since 16 is a factor of 80 and 64. And this will reduce our polynomial down quite a bit. We can actually try to factor it now. The negative 16 goes away. We can divide both sides by negative 16 immediately to get rid of it. Alright, they decided to factor it first, and now it's irrelevant. Just simply, it's only going to be 0 wherever the factors are equal to 0. Both of these two factors, or one of them could be 0. So we're getting t is 1 and t is 4. Alright, so we have the two critical values, and now we're going to have to set up an interval. Our interval is going to be from 0 to 5. Keep in mind that t is always positive, starts at 0 and increases. So we do have three intervals. The three intervals are from 0 to 1, 1 to 4, and 4 to 8, 4 to infinity. And what we're trying to do is find that interval, or which intervals for which it will be positive, greater than 0. So let's continue. We're simply going to have to test some points now. And when we test the points, you will see that after the test points were evaluated, it's only true for the original one. If you plug, say, 2 in to the original function, it turned out to satisfy it. So the object will be more than 64 feet above the ground between 1 and 4 seconds, excluding 1 and 4 entirely. Okay. And we did that simply by testing a point, and it worked. If we tested a point in the other intervals, it would have been negative throughout. Okay, now that's the end of the PowerPoint lectures, guys. And now what we'll do is take a look at some problems from the assignment. Let's look at question 1. It says solve the polynomial inequality and graph the solution set on a real number line. Express the solution set in interval notation. Let me zoom in a little bit on this. Let's make sure we can see this, guys. This is a really good problem. So we have x squared minus 12x plus 35. Okay, so it's already kind of set up for us, but what we're going to have to do is solve this guy on a number line. So let's actually work this out. I have x squared, and let's make sure that we're getting the correct equation. It's x squared minus 12x plus 35. So we have minus 12x and then plus 35, and it was greater than 0. Now it turns out, does this factor nicely, or shall we use the quadratic formula? Well, think about 7 and 5 combination. That negative 7 and negative 5 actually works. What two numbers multiply together to give me positive 35? And when I add those two numbers, I get negative 12. So it turns out I can factor this into my two factor pairs are negative 7 and negative 5. And so my critical values will be 7 and 5. And that implies that I can create on my number line these 2 points here, and it divides my number line into 3 regions. So my test point will be, I'll test, I'm going to test 0, I'll test 6, and then I'll test 8. And let's see what happens when I plug these values into, I'm going to plug it right in here. This is equivalent to there. So let's plug it in. Now if I plug in 0, I'm going to have a negative number and another negative number. A negative times a negative is positive. So it turns out to be true. It satisfies the inequality. It's positive. Let's plug in 6 and see what happens. Now, I'm kind of just doing it quickly. I'm just doing some mental math. If I plug in 6, I get a negative number, negative 1. And when I plug in 6 here, it will be positive. A negative times a positive makes a negative. So it's false. It doesn't even satisfy it. And it's also negative. And then also if I plug in a positive number 8 that's greater than 7 and greater than 5, it'll be positive here and positive here, which makes the whole thing true. It will be a true statement, and it is positive. And so what this all means is that, and we're dealing with a strict inequality symbol, so 5 and 7 do not satisfy the inequality. We cannot include 5 and 7. So what this means is that my interval solution set will be from negative infinity to 5, unioned with, I'll put it down here, 7 to positive infinity. And when we come back into the entry of the solution, one way to do it, and they want an interval notation, not set builder. So what we'll do is put in negative infinity to 5, and then we'll union it with 7 to positive infinity. And we'll check to see if that works, and it did. And now they want us to actually choose the correct graph that would make it work. Obviously, it's between B and C, and the difference between B and C is that in C, it uses the bracket notation where it's starting at 5 and 7. That means it's including 5 and 7. And 5 and 7 does not satisfy this inequality. If I plug in 5 or 7, I get 0. And 0 is not greater than 0. That's not a true statement. So definitely it will be this. Okay, this is equivalent to the interval solution. Okay, this is similar. Just move over the 4x and move over the 1, and then you're in business. This is also similar. Hopefully this factors very nicely for you. And the critical boundary points, you'll probably end up getting 3 of them, which means it's going to divide your, it will divide the interval into 4 sectors. Same thing there, so that's a pretty tough one. And then this one. This is a good problem. We're getting the 2 critical values will be 5 and negative 5. All right, let's see if we can actually do this problem. And I'll just do this here. So it was x minus 5 on top, and then x plus 5 on bottom. And I believe it was, we were checking to see if it was greater than 0. Let's check that again. Okay, it was. And so it's already set up for us. So our two critical values will be, I should call them little c, like it would be 5 and negative 5. So on a number line, I can put negative 5 and then 5. And so I need to test a bunch of points. I'm going to test negative 6, 0, and positive 6. And I just have to plug them into the equation and see if it satisfies it or not, or see if it's greater than 0. So if I plug negative 6 in here, I'm actually going to have negative 11 on top and negative 1 on the bottom. A negative divided by negative makes positive, so it's true. I'll put T for true. If I plug 0 in, well, the whole thing goes to 0. Actually, if I plug 0 in, I get negative 5 over 5. That's negative 1. That's false. Or negative, and that does not satisfy the inequality. Now what happens if I plug a positive 6 in there? I'm getting 1 over 11. That is still true. That's positive. And so what happens is we're getting negative infinity to negative 6 unioned with 6 actually, I need my boundary points in there. I can't put in my test points. That was a close call. Be sure to put in your test points in there, and it'll be from negative 5 to 5. And that will be sufficient. Let's look at a couple others. Use the graph of the polynomial function to solve the inequality. Well, what it will do is give us our test points, which will be the zeros. And so you can get the zeros of the polynomial function and then simply create an interval and test points within the interval. Now, as you can see, my interval, it'll be negative, positive, negative, positive. So once I move everything over, I will know if I want solutions to be positive or negative or greater than 0. Just once I move them over or not. And it looks like once I move it over, I want the solution set will be all the values that make it positive. So it will be positive from this point to this point, and also positive from this point beyond. So we'll have to get those test points. We only have one. We only have negative 2/3 and 0. But we need other test points in there. Okay, and one way to get the test point is, again, factor it, set it equal to 0, and solve it. Now, because it's a cubic, it should factor nicely for us. They're not going to torture you. Okay, another thing you could do is after you move it over, graph it, and then get the zeros in the calculator, and then it'll work out for you. And another note about this guy, bring that 2 over, and then combine them. Combine them together, guys. All right, so we're going to wrap it up here. Hopefully this was helpful, and if you have any suggestions or comments, reach out and let me know. Thanks.